Okay, ODE lecture 17, introduction to systems of differential equations. So we'll define them, talk a little bit about decoupled and partially decoupled systems, and then we'll talk about second order equations as systems. So a system of equations is just two or more equations with two or more independent variables. This is sort of a canonical form. X and Y are dependent variables. We want to solve for X as a function of t and for y as a function of t. But the right-hand side of the differential equation depends for both x and y on x and y and maybe also on t. And we'll put a semicolon there to sort of separate off the dependent variables x and y from the independent variable t. If there's no t's on the right-hand side, then it's called autonomous, right? So this is an autonomous, non-autonomous system. But it is decoupled, and decoupled means the x's and the y's don't interact. So we just solve this as two separate differential equations. dx dt equals x squared plus 1. How can we solve that? A couple of different ways, but keep in mind we can't do Laplace transforms on this because we do not know how to do the Laplace transform over product of two functions. So x times x, we don't know how to do that. The easiest way to do this, though, is just by separation of variables. Integrate both sides. Oops, integrate on the side of the equal sign. And you get arctangent of x equals t plus a constant. Or finally, my x function, which depends on t, is tangent of t plus c. For the y, we know that this is, if we guess, it'd be y equals the homogeneous solution plus the particular solution. The homogeneous solution, remember, is from the equation dy dt equals y. We ignore the part e to the 2t, and we get y sub h of t equals k e to the t. That's my homogeneous solution. Particular solution would be a guess. It'd be a e to the 2t. We find the derivative of the particular solution to be 2a e to the 2t, and we plug that in to this equation. So on the left side, I have 2a e to the 2t, and on the right side, I would have y, which is a e to the 2t plus e to the 2t. So just plug these two things into this equation. The e to the 2t's all cancel out. You can find a 1 here, and that gives me a equals 1. So y is yh plus yp. It's k e to the t plus e to the 2t. Okay. So this is called a decoupled system. It's autonomous. Which is that t does not explicitly appear on the right-hand side. X depends only on x. Y depends on both x and y. So I can solve this one first. And my solution will be a homogeneous solution plus a particular solution. The homogeneous solution, since this is 7x, will be k1 e to the 7t. The guess, since I have a 1 there, is, whoa, that's not weird. Why did my t come down here? I can actually move that. Let's put that t back up where it belongs. So my particular solution, xp, is a guess, which is just a. Xp prime would be equal to 0. So I plug that in on the left side. 0 equals, I plug the a in for the x on the right side. 7 times a plus 1. So a equals minus 1 over 7. So our solution then is, I'll put it up here, x of t is k1 e to the 7t minus 1/7. Okay, what about dy dt? We'll need a y of t here later. Well, dy of t dt, dy dt is 3y plus x, but now we've actually solved for x, so that's k1 e to the 7t minus 1/7. So what's y? Y is going to be a homogeneous solution plus a particular solution. The homogeneous solution is k2 e to the 3t, because we already used k1 for x. And then the guess would be a e to the 7t plus a constant. If we come up here, we can say that yp prime will be equal to 7a e to the 7t. The derivative constant is 0. Plug that in. dy dt is 7a e to the 7t. 3y is going to be 3a e to the 7t plus b plus k1 e to the 7t minus 1/7. So if I gather all my e to the 7t's on the left side, I'll have 4a minus k1 e to the 7t equals to b minus 1/7. Oh, 3b, because this entire guess gets multiplied by 3. 3b minus 1/7. Great. So the left-hand side depends on t. As t changes, the left-hand side changes, but the right-hand side is a constant. So the only way that can happen is if this is equal to 0. Or a equals k1/4. But that makes the left-hand side equal 0. That means this has to be equal to 0 as well. 3b minus 1/7 equals 0. And so that means b has to be 1/21. So y of t turns out to be its particular solution, its homogeneous solution, k2 e to the 3t, plus the particular solution, which is k1/4 e to the 7t plus the constant 1/21. And that's supposed to be k1. There we go. So a partially decoupled system, you can solve one for x, plug it into the other one, and then solve that one for y. And now we have a complete solution of that. Now, second order equations can be turned into systems of equations, and we do this by setting y prime equal to v. So we're going to introduce a new variable. We want to be able to write this as y prime equals stuff and v prime equals stuff. And this stuff should be some function of v and y, some function of v and y. Okay, so set v equal to y prime, then v prime equals y double prime. But from this equation, y double prime is equal to minus 5y prime plus 6y. But we've set v to be y prime, so that's equal to minus 5v plus 6y. So what's our system of equations? Y prime equals v, y prime equals v, v prime equals, that's here, all of this, minus 6y minus 5v. And so that gives us a way to think about second order equations in terms of system of two first order equations. We got rid of one derivative. Instead of a second order derivative, we've got first order derivatives, but the penalty we have to pay is now we have two first order equations, and it's not partially decoupled actually, because this y prime depends on v and v prime depends on both y and v. So we would need some methods of solving system of equations to solve this thing. Okay, so we're interested in these kinds of systems, right? And notice that this equation is of the correct type. So we want to rewrite this system in matrix form. How can we do that? Well, we know the right-hand side. I'll do it over here. The right-hand side, ax plus by over cx plus dy. If we think about that as a vector, we've seen that enough to be able to recognize it as that. So I'll call this matrix here M. It's a matrix of constants. This is x, y. We'll call that capital Y. The left-hand side, then, if we think of that as being a vector, it's dx dt, dy dt. What that is the derivative of something that's got components x and y, and that's my vector capital Y. So we get dy dt equals my. We can rewrite it as matrix form. Matrix coefficients is a, b, c, d. Y is a vector. And so now we have a nice matrix form for that. So example 3 was this: y prime equals v, v prime equals minus 6y, y prime equals v, v prime equals minus 6y minus 5v. So if I write this in matrix form, y prime v prime equals v minus 6y minus 5v. And I want to see if I can think of this as a thing on the right-hand side as being some kind of a matrix. So I'll rewrite it as 0y plus 1v minus 6y minus 5v. And we can see that that's 0, 1, minus 6, minus 5 times yv. So if we set y, capital Y, equal to yv, and m equal to 0, 1, minus 6, minus 5, then the derivative of y equals m times y. That's what this equation is. Note, incidentally, for example 3, right? If we go back up to example 3, what's the characteristic of equation of this going to be? R squared plus 5r plus 6. So r squared plus 5r plus 6. To find eigenvalues of the matrix M, I don't know where my pen went. What do? We subtract lambda off of the main diagonal. Think of that as a matrix and try and calculate its determinant. Set it equals 0 and solve for lambda. So what equation do we get? The determinant of this, well, multiply the minus lambda times the minus 5 minus lambda. That gives me a lambda squared plus 5 lambda, and then minus 6. So plus 6 equals 0. So the characteristic equation that we saw back in when we were dealing with second order equations, the characteristic equation we saw is the same thing as the eigenvalue equation. So, and that's why those R's were called eigenvalues. Okay, so Linearity means y1 and y2 are solutions, so is k1 y1 plus k2 y2. So if we have y prime d by dt of y, d by dt of my vector y equals m times y is our system. Suppose y1, y2 are solutions. What does that mean? That means that the derivative of y1 is m times y1, derivative of y2 is m times y2. So how can we show that the sum k1 y1 plus k2 y2 is a solution? Well, something is a solution if its derivative equals m times y. So what's the derivative of k1 y1 plus k2 y2? That's k1 times the derivative of y1 plus k2 times the derivative of y2. That's supposed to be a d. Derivative of y1 is m times y1, so that's k1 m times y1 plus k2 m times y2. And so that means we get m times k1 y1 plus m times k2 y2, because we can move scalars in and out of matrix and vector multiplication. And that's m times k1 y1 plus k2 y2. So derivative of this thing is equal to the matrix times the same thing. So k1 y1 plus k2 y2 is a solution. In terms of span, that means if I have two solutions, y1 and y2, then the span of the two solutions, all linear combinations of it, that whole thing is a solution space, they're all solutions. Okay.